Well, everybody, we have made it to our last final module of the semester, of our last 2 years together, and we're finishing up the second half of Chapter 9. We're going to focus really on estimation and how we can make things as accurate as possible, and when we can't be accurate, how much of an error we are willing to live with. So we're going to start with approximations today with techniques of linearization, which you already know, and then we're going to talk about quadratic approximations also. So let's get started. Linear and quadratic approximations. A linear approximation is a tangent line, and a quadratic approximation is a parabola that can approximate a polynomial or any other function. All right, let's start with linearization. So if the function itself is differentiable, then we've defined the linearization in the past as the equation of the tangent. So we start with the slope, which is done with the first derivative, times x minus a, plus the y-intercept. Okay, that's just the format, the y value of the point that we're looking at. So that's the format. It's the same thing as doing a tangent line where you find a point and a slope. A is what's called the center, and so we establish A down here, and that's where we're centering our linear line connected to the curve of the parabola. So what a linearization and the function share is they share a common point, and they share the common slope at that point. So just for review, we are going to find the linearization of the cosine curve at the point pi fourths. Now just for context, the value of pi fourths is, I had it here, just a second, 0.785398. And we're going to use this to estimate cosine of 0.75. So 0.75 differs from pi fourths by about 35 thousandths, okay? So let's find our linearization. So the linearization is the derivative times x minus the value plus the y value. So ours is the derivative of cosine, which is negative sine, at pi fourths, times x minus pi fourths, plus the function value, so the cosine of pi fourths. So we're looking at negative rad 2 over 2 times x minus pi fourths plus positive rad 2 over 2. So this is the linearization, and we can use this linearization to estimate 0.75. So we're going to say that the cosine of 0.75 can be estimated or approximated by the linearization of 0.75. So we're going to plug 0.75 in. So negative rad 2 over 2 times 0.75 minus pi fourths plus rad 2 over 2. And using a calculator, we get that turns out to be 0.732. Now, is this an over or an underestimate of the actual value? Well, looking at where the tangent line would come, tangent line is going to come down, skim through that common point with a common slope. Now, 0.75 is less than pi fourths, just by a tiny bit. But it is less than, and so it is going to be on the negative concave side of the curve. And so that means that the linearization, that the actual value of cosine is going to be less than the linearization of cosine. So we would say that cosine of 0.75, the actual value, is less than the linearized value of 0.75. Now, we have the luxury of a calculator, and we can figure out exactly what the cosine is. And cosine is 0.7316, and our linearization was 0.732. So yes, our cosine value was smaller, but not by much. Okay, the difference is so small that it starts to be negligible. Now, could we make our approximations even closer? Well, that's where we're going to pull in something called a quadratic approximation. So we're going to go up a degree. We're going to go from a linearization of degree 1 to an approximation of degree 2, and we're going to make it quadratic. So how do we build that? Well, you've got a formula here, and I want to kind of show you the pattern of the formula so you can work your way backwards. I want to start actually at the end. Imagine that this had an x minus a on it. That's going to be to the 0th power. Okay, that is the original value of f of a. Then we're adding the first derivative times x minus a to the first power. Okay, so that's the linearization piece. Now what makes it quadratic is that we add on the quadratic piece of power 2, and then we've got the second derivative, and we have a half of that. So it's half of the second derivative times x minus a to the second. Now in the next lesson, tomorrow's lesson, I'll explain to you why that is. But for now, I just want you to believe me that we're going to build it with half of the second derivative times x minus a squared, plus all of the first derivative times x minus a, and then plus the original value of the function. So a quadratic, for accuracy values, squeezes right in between here and hits that point. Okay, so the quadratic kind of fits between, is sandwiched between the original function and the linearization, making it even more accurate. So the quadratic and the function not only share a point and a slope, but they also share the concavity as well, which makes it that much more accurate. So let's revisit this same question, and let's see if we can build a quadratic approximation. So the quadratic approximation will be half, and we want the second derivative, which is negative cosine of pi fourths, times x minus pi fourths squared. And then plus the linearization that we already had, which is negative sine of pi fourths times x minus a, which, x minus pi fourths. Okay, and then plus the original function, cosine of pi fourths. And we're going to plug in 0.75 into that. So that'll be 1/2 times negative rad 2 over 2 times 0.75 minus pi fourths squared minus rad 2 over 2 times 0.75 minus pi fourths plus rad 2 over 2. And then you would pause and use your calculator to evaluate that. And with the calculator, we get 0.73125. And then how does that, compare to that actual value that we were looking for? So remember that the actual value of cosine 0.75 was 0.73168. All right, so we're still under, but we're even more accurate than we were before. Okay, so let's put ourselves at a different spot on cosine. Let's find the approximation, a quadratic approximation on cosine at 0, and then we're going to use it to estimate cosine of negative 0.1. So our quadratic approximation is going to be 1/2, and the second derivative of cosine is negative cosine of 0 times x minus 0 quantity squared plus the first derivative, so negative sine of 0 times x minus 0 to the first, and then plus the original value, cosine 0. And we're going to plug negative 0.01 into that. So we've got 1/2 times negative 1 times negative 0.1 minus 0 squared. And then the sine of 0 is 0, so that'll take that whole thing out. And then plus the cosine of 0, which is 1. Okay, so we're looking at negative 1/2 times negative 1/100th squared plus 1. Negative 1/2 times 1 over 10,000 plus 1. So very, very small number. Specifically, we're looking at 0.9998. All right, so we are looking at a quadratic that is going to be up here at 2. It's going to be a parabola. Okay, this is a parabola that mimics the shape of cosine. Let's see if I can maybe make that a little better. But is a parabola. So whereas cosine might come down and then cosine will change, the parabola will keep going down. But at negative 0.1, we are very, very close to being accurate of what our estimation is going to be to find the cosine of negative 0.1. So we would not say that this was equal, but we would say that the cosine of negative 0.01 is approximately 0.9998. All right, so one more time. Let's going to find a linear for a new function now. This is the natural log of the sine. Okay, and we're doing it at pi/4, and we're going to compare it to the actual value of 0.8, which is a little bit larger now than pi/4. Okay, so a couple things we might want to do ahead of time that will help us. If we're working with this derivative, or this function, let's figure out the first derivative ahead of time. So it'll be 1 over the sine of x times the chain rule, which is cos x, so that is cotangent. And then f double prime, which we'll need for the quadratic approximation, is going to be negative cosecant squared of x. So those values might be helpful to us. All right, so we'll kind of tuck those aside. Okay, our linearization will be the first derivative, so the cotangent of pi/4 times x minus pi/4 plus the original function, so the natural log of the sine of pi/4. Our quadratic approximation is going to be 1/2 of the second derivative, which is negative cosecant squared of pi/4. That value, times x minus pi/4 to the second, and then plus the linearization, so then plus whatever we get for L of x. Okay, so then let's plug 0.8 into both of these to get an estimation. So the cotangent of pi/4 is 1 times 0.8 minus pi/4 plus the natural log of the sine of pi/4, so the natural log of rad 2 over 2. And so the decimal value of that, let's check that out, turns out to be negative 0.33197. Okay, so my quadratic approximation would be 1/2 times, now the cosecant of pi/4 is 2 over rad 2. So squared, that turns out to be 2, so we have negative 2, times 0.8 minus pi/4 to the second, and then plus the value we got for our linearization. All right, so let's see what that comes out to be. And I get negative 0.33218. So with a linearization, we get something, the quadratic approximation is going to be a little bit higher than the linearization. So let's compare that to the actual value of f of 0.8 here, of f of 0.8. So we're just going to plug that directly in because we have the luxury of a calculator. And we get negative 0.33218. Okay, now technically that was a 4 and this is a 3. So that's the difference between these, is the accuracy of a quadratic approximation is just amazing if you're close to your original target value. All right, so we're setting the stage for doing higher orders. We've just done linear and quadratic, but we're going to learn how to make cubic approximations, and we're going to move our way on through, and each time getting more and more accurate. Now, you might wonder, like, why are we doing this if we just have a calculator? Okay, well, we just got to rewind back to when these were developed. They didn't have calculators, and so they were doing all of these computations manually. And it was much easier for them to work with polynomials if they could turn it into a linear or a quadratic or a cubic that was going to be sufficiently close, than to work with a trig and a logarithmic function. So we have the luxury of having a calculator, but we're going to be studying this so that we can understand where these came from. All right, I'll look forward to seeing you guys on Thursday, and I hope you have a good middle of your week.